Welcome to our third session of the hydrogen unit for our Run on Less Messy Middle Bootcamp series. My name is Rachel. I am the Industry Engagement Manager with NACFE and the moderator for our last bootcamp session today. If we could go to the next slide. This is our last formal session, so I just want to extend an extra thank you to the team over at ACT News. They've been a fantastic team member and resource to us as we've gone through the bootcamp sessions starting all the way back in mid-February. I cannot encourage you enough to make sure to subscribe today if you are not already. If we could go to the next slide. As I had mentioned, this is the third session of our hydrogen unit. And while, yes, this is our last formal session, we will be back in 2 weeks to host the hydrogen workshop, which will not only serve as the workshop for this unit, but also serve as the finale for the bootcamp series. Together, we'll be covering highlights from the bootcamp. We'll from some of our team members that are on the ground conducting site and the interviews with the teams responsible for keeping these vehicles going. And we'll be discussing some preliminary conclusions about what we're learning through this process. So in true workshop fashion, attendees are going to have the opportunity to participate. You will have an invitation sent to your email, so be sure to register. If you don't see this link and you would like to attend, you can reach out to myself or Stefan and we will get you registered. Let's go to the next slide. So speaking of our team on the ground doing our site visits, the team is still hopping around the country, gathering everything that there is to know about these fleets and their experiences running these vehicles. Make sure that you stay tuned for our fleet profiles that will begin release at the beginning of August, where we'll be sharing what we've learned so far before the actual run in September. If we could go to the next slide, I'd just like to extend a thank you to our sponsor for today's session, which is HydroFleet. So thank you very much, HydroFleet, for supporting Run on Less and helping to make this demonstration, this very important demonstration, possible not only for NACFE, but for the industry as a whole. Next slide, please. We'll just talk very briefly about the quiz. So if you head back to the landing page for this session on runonless.com, you can take the quiz. It will be available immediately following this session. This is your last opportunity to receive a 100% on your quiz and enter your name into a drawing for some Messy Middle swag. So remember, you get 1 submission per passing quiz for a max total of 9 entries. You'll see the Google form to provide this information once you receive that 100% today. Next slide will be our final reminders before we get started here. This session is being recorded. It's going to be posted online later this week. It usually is posted on Fridays. Questions are encouraged during the session. Your Q&A controls are going to be in the upper right-hand corner of your screen. And finally, Stefan Babcock with ACT News is here to troubleshoot any problems that you might have. His email is here on the screen, so make sure that you reach out if you're having any technical difficulties today. And with that, we can go ahead and get started. We can go to the next slide, and I'd like to introduce you to our third hydrogen session panel. Thank you so much, panelists, for being here today. Our first presenter today is going to be Tarek Abdelbasset. Tarek is the Director of Business Development for Hydrogen Storage Systems at Forvia. Tarek, I will pass it over to you.
All right, thank you. Okay, so what I'm going to do is I'm going to give the group here a general presentation on the different forms of hydrogen storage out there. You're going to hear today from a group of OEMs and Tier 1 suppliers, such as ourselves, on what we do, how we do hydrogen storage, how we do different hydrogen vehicles in general. So you'll get a couple of different technologies on the vehicle in general. So moving on to the next slide, please. I'll give you a very quick summary of just who we are for VIA. We're a large Tier 1 supplier, so we supply globally all the major OEMs. 1 in 2 vehicles today will likely have a part from us in it. We have multiple divisions, so all over the vehicle, there will be different groups and different commodities that we serve. Today, we're number 1 in traditional exhaust systems, and as we see that business declining as we electrify more, it's our ambition to become number 1 in hydrogen storage. It's a commodity that in many ways carries over well from our ability to weld steel, our ability to handle composites in some of our other interior divisions, etc. So we saw that as our opportunity to transition to a clean technology offering. Okay, next slide. So where and when do we want to do fuel cell vehicles? This used to be a really big debate. It used to be basically batteries against hydrogen. But in the last, I'd say, 5 or so years, it's really settled down to a very complementary type offer. It's not a this or that solution. It's a this and that type solution. And what it kind of boils down to is as the vehicles get larger, kind of with a crossover point of around a class 3 vehicle, it starts to favor, on average, a fuel cell offering. The main reason being is a fuel cell or a hydrogen type vehicle offering is what we call kind of a 3-box solution, whereas a BEV is a 2-box solution. So a BEV is a battery and an electric motor. A fuel cell or a hydrogen vehicle is usually a tank, a motor, and or an engine, etc. For example, so there's always that extra box that you got to package for when you're dealing with hydrogen, and so that's why in smaller vehicles, BEVs tend to fare better, whereas on larger vehicles, the package, the amount of range that you can get, the amount of payload that you can get, and the recharge times when you're trying to charge that much fuel tend to start to favor a hydrogen, a fuel cell, or even an ICE type solution. The same can actually be kind of partially true for infrastructure. As we get to bigger and bigger vehicles, relative to a battery, we need more and more power off the grid, which can become an issue to solve. Whereas with hydrogen, it looks more like a traditional fueling experience where you kind of up in 5 minutes, fueled from 5 to 10 minutes, and you're not straining the grid. So there's kind of a decoupling from the grid. So again, as the application gets bigger, the infrastructure starts to favor more and more a hydrogen type solution. Next slide. Okay, so overall, why hydrogen? So hydrogen is what we call an excellent energy buffer. It's really good for applications where there's intermittent high power type needs. So vehicle filling is kind of one of those examples. The more renewables we see on our grids, where we see wind and solar kind of happening intermittently, hydrogen becomes a really good way to store that. So in the grid, in the overall energy grid, and on larger vehicles, like we said, we see an overall picture where hydrogen can account for about 20% of the total energy grid, which includes transportation, but also other industries like steel, fertilizer, etc. The other thing that works kind of regionally well too is there's a pathway. There's multiple ways to make hydrogen and multiple ways to move hydrogen. So there can potentially be a solution for anybody wherever you are in the world in terms of what feedstocks you have available to you. Okay, next slide. The next slide will kind of describe all the different ways out there of storing hydrogen, from kind of the more traditional to some more exotic versions. But you'll see kind of four main categories here. The physical type storage, which you'll see on most of the vehicle offerings today, which is compressed gas, cryocompressed, and liquid. Cryocompressed is really kind of the middle point between a pressurized and a liquid cold cryogenic type system. Then there's a whole class of materials-based solutions where you store hydrogen like a sponge in different materials. And there's literally hundreds of different materials that are under study out there. The ones I show below are just kind of some of the top hitters in some of the different classes. We won't go into that today at all. Today we're going to focus for the most part on compressed and on liquid, which are probably the two most near-term solutions, and which you'll probably be hearing from some of the other panelists today too in terms of their offerings. Okay, next slide. So the first one, which will probably be the most common one that you'll see in the near term, is compressed hydrogen. Today, we to get enough density for kind of a usable range on the vehicle, we store anywhere between typically 350 bar, but more commonly now we're going all the way up to 700 bar, which is basically a 10,000 psi system. So incredibly high pressures. To get to a tank that's not insanely heavy, we're using a lot of carbon fiber. So these are all composite wound tanks. Um, and so some of the advantages of this is it's a relatively simple system, behaves for the most part just like you say a propane or CNG type vehicle, which we have a lot of experience with in the market today. It fills quickly for the most part. Feels almost kind of on average, in terms of fill time, like a diesel experience. And it is and it is very safe actually. There's many videos you can watch online where you see the crash tests and everything being done with the tanks. The tanks themselves are usually a lot stronger than all the metal and the vehicle around them that tend to crush around them. The drawbacks, however, is carbon fiber is expensive. The overall storage density is going to be the lowest of the other, the three options you're going to see on this page. So the ranges you're going to get in the vehicles are not quite yet comparable to a diesel type range. So the systems will be bigger with less range than a diesel current equivalent today. And you do use up a bit of, compressing to 10,000 bar does use up about 20% of the actual energy value of the hydrogen itself. So it's a non-negligible amount of energy when it comes to the full energy pathway. Moving on next to liquid. Liquid is an option that can give you, for the same amount of space, 2 to 3 times more fuel, depending on how big the system is. So it's an immediate tripling potentially of range for the same amount of storage tank. So that's kind of the immediate the immediate benefit of it. The With liquid though is it's a very much a use it or lose it type proposition. If you don't use hydrogen, if you don't use the liquid hydrogen because it's at really really cold temperatures and heat creeps in eventually, no matter how well you insulate these tanks, you're going to start losing potentially up to 1 to 2% of that hydrogen per day for every day you're not using that tank. You don't need to use much to keep it cool, but you need to use it. That's the big thing. So for applications like long haul trucking, where there's high uptime on trucks, this is a very viable solution, and you'll see that from some of the others today. If you have an application where the vehicle or the truck parks for any extended period of time, you're probably going to want to stay with some kind of a compressed system where there's no loss because of sitting. Okay, moving on next to cryocompressed. Um, Cryocompressed is kind of an in between of both worlds. It's compressed and it's also cold at the same time. You get even better yet densities of hydrogen storage. But as you can imagine, making something cold and pressurized is a very complex system. Um, you can have reliability, etc. Is a very difficult thing, and the inconsistency of kind of fills. You may not get 100% fill every time, depending on how hot the system was coming in and how empty it was, which is something that's usually not desirable to a customer. Usually, you want to fill up, you want to know that your tanks are 100% and you're going to get X range. So that's one of the complexities of dealing with something that's it's a two-in-one shampoo. You shampoo conditioner. You never really get the best of both worlds. Okay, moving on next.
Tark, we've got about 30 seconds left for final points.
Okay. All right. So just quick offering in terms of what we do is full tanks to all the way to full systems. Maybe we'll move on to the next one in terms of offerings. Okay, and then the last basic slide here is partnerships. We like to push partnerships. So you'll see that here that we partner with Symbio. So Symbio is a joint venture between Stellantis, ourselves, and Michelin, which offers the fuel cell engine. We also partner with Symbio, you'll see in the top right corner, to offer a Class 8 truck here. This is a drayage truck, kind of a minimum viable solution, about a 250-mile range drayage truck with no payload loss. And you're going to see other solutions today and other partnerships. Everyone's got a little bit different flavor from the rest of the speakers that we have. And the last thing to emphasize is that we can do the same for H2 ICE. So in the top left corner, you'll see a project we did with Southwest Research on H2 ICE. So it doesn't dramatically affect our systems. And again, the same tanks for the most part we can apply in the bottom left corner here for moving hydrogen in bulk transport. So that down below you see a partnership with Biotech to move about, that trailer, that 20-foot trailer, about a 500 kilogram type system. So just give you a sense of the partnerships and where we're participating, trying to bring you the vehicle and the fuel. And you'll hear several from our partners today and our panelists. You'll hear similar things. So with that, I'll end. Thank you.
Thank you so much, Tarek. So the second presenter today is Hui Xu, the technical project leader of Global H2 ICE for Cummins. Hui, thanks so much for being with us today. The floor is yours.
Thank you very much, Rachel, for the opportunity for us to come in and talk about the Cummins hydrogen internal combustion engine. I want to mention our co-author, Iman. Iman is in the audience today. He's our general manager of Turner Fuels and the fuel delivery systems. We will have the contact information in the end of the presentation. Reach out to us if you have question that is not addressed from this panel discussion. Next slide, please. Next slide, please. Yeah, so just a little background. Cummins is the world's largest independent engine manufacturer. We recognize the needs for the greenhouse gas reduction as well as the world needed the power. Right? So the Destination Zero is our initiative to lead to the zero emissions future, where we can also continue providing the power that would the world would need. And hydrogen internal combustion engine is one of the technologies we have been working on. Next slide, please. So Cummins actually operating in a pretty wide range of applications, at least a few at the bottom. We actually work on the both on-highway and off-highway applications. We do see the interest from both on-highway and off-highway, just to list a few. The regional haul, line haul, vocational constructions. And if you look at those applications, and just look at which fuel get the work done today, because diesel is versatile, is reliable, low cost, is widely available, is a pretty good fuel to use. But with the motivation of the reduced greenhouse gas, we noticed, we're getting into this messy middle. For the low load and low operating hours, the BEV definitely is the way to go, just like Tarek mentioned. But when we get into the hard to abate sectors, hydrogen technologies does play a significant role. I want to mention both the hydrogen fuel cells and hydrogen internal combustion engines, among other fuels like the renewable natural gas and diesel. And if you go to the next slides, we'll talk about a little bit of on the hydrogen ICE. So hydrogen ICE, by definition, this is basically internal combustion engine fueled with hydrogen, right? So for Cummins, this is our spark ignited engine variant. It would be similar to the natural gas and gasoline product we have on the market. It does utilize the existing installed capacity in the engine and component manufacturing, and it will extend the internal combustion life, and it is complementary with the fuel cell like the other panelists mentioned earlier. I do have two tables out of the bottom just to address this a little bit of more details. So on the first table on the left-hand side, we are showing diesel, hydrogen, natural gas, and gasoline. They all share a lot of base engine and the installation parts in there. Between hydrogen and natural gas and gasoline engines, they share a lot of commonality in their cylinder head, the ignition system, the engine control modules, and their softwares. Hydrogen does have a unique fuel system and air handling system, which I will introduce in the next slides, and its after treatment system actually share a lot of commonality with our existing diesel product in there. So it does provide a really complementary to develop the hydrogen when we already have the diesel and natural gas product. So the second table on the right hand side is comparing the hydrogen fuel cell and the hydrogen engine. They do share a lot of commonality in terms of the hydrogen production, the distribution, the fueling stations, and the onboard storage. And hydrogen ICE is believed to have faster path to the market. I think working on the hydrogen engine can potentially improve those infrastructure for the fuel cell as well. There are two differences between the hydrogen and fuel cell and a hydrogen engine. The first one is the hydrogen fuel cell does need the electrification of the driveline and accessories in order for it to be used for the transportation. Hydrogen ICE does not require the electrification. It can use the existing drivelines and accessories. The second thing is the fuel cell does not need the emissions after treatment to meet the criteria emissions. Hydrogen ICE though, it does require the emissions after treatment. If you go to the next slide, I have more information talk about how Cummins look at the hydrogen engine architecture. So we are working on the medium duty and heavy duty hydrogen engine as we speak. So we are having similar architecture considerations to commonize their architecture. I want to point out our base engine as our part of the HELM platform, the HELM, which is the high efficiency, low emission, and multiple fuels engine platform for spark ignited engine. We do have the advantage of having a pan-roof tumble system. So this offers a unique opportunity for us to be able to use the direct injection hydrogen, and that one brings the benefit of safety as well as the power density advantage. We also chose the lean burn air fuel ratio compared to the stock, bringing in much better efficiency. But when we go into the lean burn, we do need a lot of air. So this is the partnership with our internal Cummins turbo technology to identify the turbo options to deliver the air we need from the steady state and the transient as well. We also partner with our valvetrain, internal valvetrain partners to optimize the valve profile to balance between airflow and the abnormal combustion. On the ignition system, we do not need unique ignition system, but the considerations need to be given to the ignition systems are we do need the cold spark plug to reduce the abnormal combustion from the ignition system, as well as we need to meet the spark plug life expectation since this is lean burn. And since this is the lean burn, we also need the diesel-like after treatment, like a urea SCR to control the criteria emissions in there. And in the lab, we are able to meet the global emissions using the SCR system. The crankcase ventilation system is another unique thing for hydrogen. Hydrogen has a really low ignition energy and pretty wide range of flammability range compared to other fuels. For that one, we ideally we don't want any air fuel mixture other than between the intake valve closure and the exhaust valve opening. But the crankcase, we inevitably will have some blowback from the power cylinder through the piston rings. So we need to actively maintain the hydrogen concentration to the safe level. But when we do this one, we actually were able to manage the moisture really well in the crankcase. So last but not the least, the engine control module. So we developed the engine control module hardware and the software to be able to pull all the components together to achieve the diesel-like power density and the efficiency, and does share a lot of commonality with our natural gas product as well. So if you go to the next slide, like I mentioned earlier, we are working on the next slide, please. Also working on the medium duty and heavy duty. The heavy duty, medium duty is 6.7. The heavy duty is a 16 liter. I wouldn't report the power and torque range. They are comparable with the current the diesel product. We do target to meet the global emissions level. I also wouldn't repeat the architecture, but I do want to point out the unique Helm platform offered the tumble system enable us to be able to run the direct injection and lean burn to achieve the power density and the efficiency we need for our customers. So next slide, please. And the question is also, what does the vehicle look like? And I'm showing a heavy-duty vehicle installation example here. This is a Class 8 sleeper cab and targeting users with a large fleet in there. Again, 16-liter engine in this specific example using the Endurance AMT. And there are parameters, the other parameters are similar to the current product, diesel and natural gas. I do point out a few things on the left chart in there where the hydrogen engine installation, it aligns with the diesel and the natural gas. And once again, also the hydrogen engine integrates with the current transmissions, the driveline and chassis. It does not require the electrified system in order to be used for the transportation. We're thinking we can safely package like 80 kilo of hydrogen in there and comfortably support 500 miles on the daily range. Yeah. So if you go to the next slide, and that would be my last slide, we are providing there's a link you can get more information. Once again, thanks to my co-author Iman, and you can find our contact information from this one should you have questions after the panel discussion. Thank you very much.
Wonderful. Thanks so much, Wei. I will call you back when we do our Q&A. And our next presenter today is Ben Hapik, who is the General Manager of Commercial Vehicles and Hydrogen at Hyundai Motor America. Ben, thanks so much for taking the time to be here with us today. I'm going to pass it over to you.
Thank you so much, Rachel, and the whole NACFI team and the opportunity to present here today. So we are very pleased to announce, and I think that has been announced by you already, that Hyundai will be inserting 2 trucks for the upcoming Run on Less, one with Pilot in Southern California and one with Penske Logistics in Texas and Arkansas. And this presentation is meant to give you a little bit of background on what we have been doing and are currently doing with regards to fuel cell Class 8 trucking in the United States. Next slide, please. So Hyundai's development background for fuel cell and fuel cell powered vehicle goes back to 1998, where we basically initiated development of our own captive fuel cell system. We are one of the few OEMs that can claim that we have a very high level of vertical integration when it comes to developing the base vehicle and also the associated fuel cell powertrain. The first prototype vehicles have been tested in Hawaii in 2000. That was our fuel cell powered Santa Fe. SUV, and then the world's first serial-produced fuel cell vehicle, the Tucson FCEV in 2013, followed by the Nexo, which is still on sale here in California. And then in 2020, the first serial-produced fuel cell electric truck, Axion fuel cell, with deployments in Europe. We are also producing fuel cell powered transit and coach buses. And since 2023, we also have a fuel cell powered Class 8 tractor, Axion fuel cell 6x4 tractor here in North America. Next slide, please. So when it comes to the European deployment, which I was working on back in 2018, so that's now a good solid 7 years of development on this truck, we have been accumulating about 8.3 million miles in customer operation. We have 49 trucks on the road, and we have been proving that this technology is highly reliable and works really well, with the fuel cell system actually lasting longer than we initially expected. The fuel cell itself is coming from our Nexo light-duty product, but has been upgraded with regards to durability to meet the heavy-duty trucking demands. And we got fantastic customer feedback, quoting low noise and vibration, obviously similar to a battery electric truck. This is a very silent vehicle to drive, very comfortable to drive. We had no major breakdowns or quality issues. And what people often overlook, the cold weather performance. Switzerland gets quite cold, has been excellent. So we lose maybe a couple of % of range during winter months, which cannot be said about battery electric trucks where you need a lot of power to heat the cabin. This can all be done here with a fuel cell truck with waste heat that we capture from the fuel cell systems, which operate at about 60% of efficiency. Next slide, please. So this is an overview of our heavy-duty truck, the Axion fuel cell. You can see that below it's a cab-over engine European-style truck that we quickly adopted to be quick to market here in the United States. We have replaced the diesel engine, which was typically located under the cabin, with a fuel cell system derived from our Nexo, 90 kilowatts. And then there's a second fuel cell system under the tank rack that you can see behind the cabin. So we have a total of 180 kilowatts in combined stack power on the truck. We also have a 72 kilowatt hour high voltage battery that is together with those fuel cell systems powering the vehicle. Think a kind of a hybrid setup, which also gives us an ability to recuperate energy when braking or coasting. So we have a 300 kilowatt Dana TM4 drive motor here that we can again use for recuperative braking. We have this system is coupled to a 6-speed Allison transmission. We only use 5 of those speeds, so we say it's a 5-speed automatic transmission here. That is actually coming from the diesel world still. And then we have a hydrogen tank rack here that you can see behind the cabin with about 68.6 kilogram of usable hydrogen. So the old system size is 70 kilograms. And this hydrogen storage system allows us to achieve a driving range of about 450 miles. It goes higher depending on payload, obviously. We have seen our customers running as far as 510 miles with the truck. But that was at GCWs in the range of 70,000, 72,000 pounds. At 82,000 pounds, which is the legal limit here for a fuel cell truck, we achieve driving ranges in optimal conditions of about 430 to 450 miles. Another advantage that has been quoted before is the refueling time. So in only 30 minutes, 20 to 30 minutes, depending on the performance of the refueling station, we can be back on the road and drive another 450 miles. So that's, I think, a major advantage of those fuel cell electric trucks. Next slide, please. So this is a little bit about our model year enhancements that we are introducing this year. So the Axion that we deployed in our early deployments did not have ADAS. It did not have a lot of other features that we have been adding on. And we will be selling the truck with all these features that you can see here on the slide. In the interest of time, please move ahead. So this slide captures the current deployments that we have in North America. So the biggest one so far, NorCal Zero project with our partners at GET Freight and First Element Fuel and CTE as project manager. So we got awarded grant funding in excess of $13 million for the whole project, and we're able to deploy 30 trucks at the Port of Oakland. But we also walk the talk in our own captive logistics in Georgia. We have now 21 trucks deployed in Savannah and are using the trucks for our own captive internal logistics. Not shown here on the slide, but I want to mention it. We also have 5 trucks deployed in Southern California with Pilot Company, and they do gaseous hydrogen distribution with those trucks, and this will be also part of the Run on Less this year. Next slide, please. So here you can see a little bit of the NorCal Zero project with a refueling station that has been built to fill up to 200 trucks per day, and doing regional haul, basically drayage operations out of the Port of Oakland, but also finished car hauling. Often overlooked are all the community benefits that come with these deployments. So we abated a lot of CO2 and criteria pollutants, which is always important to mention in front of our sponsors, of course, and also the politicians that have been so much supporting this project. Next slide, please. So for the Georgia operation, I mentioned it before, Hyundai and Clovis, our own captive logistics company, formed a new entity called H2 Logistics. And the goal here is basically to put our whole captive demand that we have in North America, which is plenty. We have 2 legacy plants in Georgia and Montgomery, Alabama, and now the HMGMA, our meta plant that builds all of our EVs. We want to transform all of our logistics to zero emissions, and that is basically the mission of H2 Logistics. Next slide, please. So for that, we are with our partner Hydrofleet, which is also title sponsor here today of this bootcamp. We are building a very significant refueling site in the city Pooler, close to our meta plant, about 15 miles away from our meta plant. And this site will be able to fuel all of our 21 trucks plus Alpha. So in our first initial step, which will go online later this year, we have about 1.2 tons of gaseous hydrogen available. And this hydrogen, and this is very special about this site, will be produced locally with an ATR system, taking in natural gas and then basically producing the molecules right where we consume them in a modular way. So we are able to add more units and more systems according to our truck deployments, and we'll have a final build out of 4.2 tons of daily hydrogen fuel available with 5 tons of hydrogen storage. I just lost my screen for whatever reason. Sorry. So I think that in the interest of time concludes my talk for today. And yeah, thank you very much for your interest.
Perfect. Thank you so much, Ben. We can still hear you and see you now, which is good. So I'll call you back during the Q&A portion, and maybe we'll do any technical troubleshoot that we need to do. But last but not least, we have Derek Rotz here with us. He's the Director in Advanced Engineering for Daimler Truck North America. Derek, thanks so much for joining us today and being our anchor presenter today. The floor is yours.
Perfect. Thank you, Rachel. Pleasure to be with you all, and excited to give you a little bit of a sneak peek what we've been doing inside of Daimler Truck North America with regard to hydrogen. And to give a little bit of a teaser, we've been obviously engaged with research programs with Department of Energy, Super Truck, initial Super Truck, and we're now on the third program, Super Truck 3, where we're focusing on basically creating a zero emissions vehicle that's suitable for Class 8 long haul. So if you go to the next slide. As you know, Daimler Truck focuses on Class 6 through 8 vehicles. A lot of our vehicles haul a lot of freight over long distances, and we've discovered that the challenge to creating a zero emissions vehicle is particularly difficult under those conditions, trying to move, 80,000 pounds or 82,000 pounds, 600 plus miles per day. It's kind of the bread and butter of our diesel world. And as we've come to learn with battery electric, there's a challenge to do that, and not only just technically on the vehicle, but also operationally. We see a lot of hurdles there. So when we set out to scope out the Super Truck 3 program, R&D program, what we wanted to do was to showcase what that ideal Class 8 long haul application looks like. We selected hydrogen, we selected fuel cells, and we decided to set ourselves some goals that would basically show how these vehicles not only could run efficiently from a TCO perspective, but also looking at the freight operations and thinking about operational efficiency. Things that don't really show up in a TCO calculation in terms of dollars per mile traveled. Things such as payload, range, refueling time, things like that are really important for operating these vehicles efficiently. So when we set out to put the goals to these programs, we said, okay, we want to have a range of at least 600 miles without compromising payload or wheelbase. We thought a driver driving 600 miles a day, 11 hours a day, is kind of the limit. We'd love to have that driver focus on the driving task and not have to stop and refuel and wait in between in the middle of their driving session. Payload, of course, the heavier the vehicle, the less the freight. So obviously we want to keep payload in focus. And then last but not least, wheelbase maneuverability. We know these vehicles have to maneuver in very tight spaces, and any growth in wheelbase reduces maneuverability and kind of renders that vehicle less useful for certain applications, certain depots, certain destinations. As I mentioned before, we focus on fuel cells. We have a joint venture company called Cellcentric that is developing the fuel cell systems for us. We're basically working with them to specify and define what a fuel cell specifically for Class 8 long haul looks like, and I'll talk a little bit more about that. Basically what we're doing is in this program we're building two prototypes. The first prototype we call a B sample vehicle. So that's our first integration of a fuel cell vehicle that we put together in. We're using existing systems and components, including gaseous hydrogen tanks, and getting that vehicle up and running, which should happen here relatively soon. We're also looking at a final demonstrator in 2027. So that would be a second vehicle that we're building that would demonstrate all of our objectives that we're setting out for in terms of range, payload, wheelbase, refueling time, and so on. And that vehicle will be focused on liquid hydrogen fueling solution, a subcooled version, which I'll talk a little bit about as well. That is sort of a standardization that we're pushing through ISO for the fueling process as well as the fueling equipment. We do want to have a lot of energy on board, so we're targeting 100 kilograms of hydrogen. We think that's what it takes to get this vehicle to move that amount of freight at that distance. And we want to have refueling time on par with diesel, so we can have this truck operate as efficiently operationally as would a diesel vehicle today. So next slide, please. And last but not least, to demonstrate what we want to do is we want to demonstrate what the full potential is of hydrogen in this space. Here's just a little bit of a specification between our initial vehicle that we're building, the B sample on the left, as well as the final demonstrator on the right. These are some standard specifications that you see on the vehicle. On the left-hand side, a couple of things I'll point out with the B sample is, we're a little bit long on the wheelbase on that end. We've got a 6x2 system. We're using a twin fuel cell system on board. It's installed behind the cab, and so on and so forth. So it's basically our first version. If you want to call it, if you imagine your first version of your cell phone that was invented, if you remember the initial Motorola's with the big carrying case and the huge antenna, and you had to go outside, that's kind of what this vehicle is. But our final demonstrator, the vehicle on the right here, I'll just highlight some pieces in bold, and you can see the renderings down below. Our goal is to really get this vehicle to diesel-like performance, dimensions, weight, sizes, and maneuverability. And as you can see on our design here, which we're about ready to complete, we are able to get that chassis down to 223-inch wheelbase, which is on par with a diesel tractor. This is including packaging that 100 kilogram tank, which goes along basically the frame rails from the steer to the drive axles on either side. We're working with Cellcentric on developing a next gen fuel cell, so a single engine rather than a dual engine, which provides a lot of benefits in terms of packaging, also efficiency. We see a big uptick in gain there. And then also because we have that next gen fuel cell, we can reduce the battery capacity by half and still maintain our basically our drive cycles, our duty cycles, not only on the flats but also in the hilly sections of the freeway system as well. And so the whole goal of this final demonstrator is to show that this is something that is optimized for a fleet that can run head to head with diesel. So next slide, please. Yeah, that pretty much concludes our section there. Stay tuned as we continue to build these things out and as we report on progress towards our super truck. Thank you.
Fantastic. Thanks so much, Derek. If I could have all of our speakers return, we'll go ahead and get into some Q&A here. We've had a couple of good questions from the audience members that we can start getting into. And by all means, folks, feel free to send in additional questions as you're coming up with them here. So the first question that I have, and this is something that was brought up, Tark, during your presentation, and Derek, you touched on this a little bit as well. So obviously in the battery electric space, there's a lot of concern about sacrificing payload for battery weight. Is there any concern about a similar sacrifice when we're looking at hydrogen storage? And what does that conversation look like right now?
I can talk a little bit from my side maybe, and then Tarek, if you want to chime in as well. So the payload aspect was something that's quite important to us, and our target with this program is to achieve payload equivalency to diesel, and that doesn't mean that the tractor will weigh the same. You do have extra benefit of going from 80,000 to 82,000 pounds, which is good. There is a lot of stuff on a fuel cell truck which does add weight, so you do use that weight as well. The others on the flip side, fortunately, you've got roughly 100 kilograms or 200 pounds of fuel when you're fully fueled up of hydrogen, and you're looking at on the order of over 1,000 pounds of diesel if you're fueled up as well. If you got 300-gallon tanks, and so the weight of the fuel itself when you're full, you're going to have some advantage with hydrogen as well. And so if you add all that up, we think we can get to payload equivalency to diesel. So, but Tarek, maybe you've got something to add.
Yeah, not too much to add to that. I mean, that is the goal, is minimize the weight. I mean, whether you're dealing with a liquid or a compressed system, they are just inherently more complex systems than a diesel tank, which is either a stainless steel tank or a blow molded plastic tank with a few kind of auxiliaries to it. So we're inherently always dealing with something going to be a little bit more complicated of a system. So there'll always be a bit of a weight penalty, I'd say, compared to the incumbent. I think, as Derek said, some of the trade-offs there that you manage as a vehicle, right? So the OEMs are, as a whole vehicle, you can find savings elsewhere. But that is the balance. It's compared to a battery, significantly, if you want a battery with that long range, significantly lighter, but we'll always struggle a little bit to match the diesel equivalency. But that's on the vehicle level for the OEMs to deal with that difficult balance.
Sure. Awesome. And it looks like we actually just got a related question. So before we move on, I will read this one here. Does a liquid storage tank in the truck require fueling from a liquid tank, or can it also refuel at a compressed system?
I can take that. You would have to, the fueling station itself would have to have it in liquid form. That's what we're envisioning today. So it would be produced, it would be liquefied at the production site, distributed as liquid, and then dispensed as well. And I didn't attend the distribution session on hydrogen, but from what I understood is that there are advantages to liquefying it in terms of the amount of energy you can fill per truck tank fill, or per truck tanker. So like there is some incentive, I believe, already to do that. And then the fueling energy, going from a liquid filling station to a liquid tank is not that much either. So, but yeah, I think otherwise, to have a compressed gas at site and then try and liquefy it at the station, I'm not aware of a lot of folks looking into that.
Gotcha. Great. So I guess we'll kind of stick with the storage piece. So this question is for Ben. Ben, if you're able to
Yep.
hear me. Awesome.
I can
Okay,
hear
perfect.
you. Unfortunately, my camera stopped working entirely, so I apologize, but I can hear and I can talk.
That is a-okay, no worries. So one of our audience members has asked, how big is the risk of having the H2 tanks behind the sleeper? Is that something that you guys are looking at? What can you tell us about the risks of that kind of configuration?
Well, risks with regards to safety, or what kind of risks?
Yeah, I'm assuming they're probably meaning safety, but whoever had asked that question, if you want to provide additional clarity, I'll watch the Q&A here.
Yeah, I can speak to that. I mean, we have seen similar arrangements with CNG for quite some time, and I would argue that those tanks are maybe even more, or what can I say? Frankly speaking, the risk is extremely low. We have crash tested the truck. The tanks itself are type 4, which means they have a polymer liner, and then there's a lot of carbon fiber wrapped around them. So they are virtually indestructible. They go through rigorous testing, which includes drop tests, which includes bonfire tests where they're exposed to fire. There are emergency release valves that, in a very controlled way, release hydrogen if the pressure rises to a certain value. And they even get shot at with a rifle. And the bullet is not to penetrate the carbon fiber. So I would say the tanks might be the most robust piece of the whole truck. And again, if there is a thermal event, if there is overpressure, the gas will be vented automatically via these valves. There is a cutout in the top spoiler of the truck, and there's a common pipe basically where all the hydrogen will be released in a very controllable way. And hydrogen is a very safe in regards to its high volatility. It just disperses. Whereas when you have a diesel flame, for example, diesel will pool on the ground. This will not happen with hydrogen. It will just go away. So
great, awesome.
For anyone interested, there's 2 good videos online, just the YouTube videos. Look up Toyota and Hyundai, and just look at hydrogen crash tests or testing. And you'll find, I mean, they're not Class 8 vehicles, but they're kind of passenger vehicles. But you'll actually see some of those penetration tests with a bullet that they mentioned, and then you'll also see a crash test, and you'll literally see both the vehicle and the impact skid crush around the tank. So these tanks have about that much, carbon fiber in them. They are significantly stronger than anything else on the vehicle.
That's great. That's a fantastic suggestion. So Ben, I guess I'm gonna keep this question for you here. Let me find it. So one of the things, and you touched on this in your presentation, I was hoping to ask about it. I'm glad that you brought it up during your presentation. But one of the things that NACFE is really proud of is kind of our focus on driver experience in the run. And you were talking about some of the features of the Hyundai truck. What is your take on kind of the similarities and differences in driver experience that we can expect? And Derek, by all means, feel free to jump in on this as well.
Well, from a powertrain perspective, I think there's not a huge difference. The way the truck behaves is very similar to diesel. One major change is that you, instead of having a control of your retarder, you basically can control with a lever next to the steering wheel the amount of recuperation you want to see. Very similar to a battery electric truck. So I would say if the drivers are already familiar with battery electric, they will feel right at home with the Axient. That again, it is a cap-over engine vehicle, which is not common in the US. was common maybe 30 years or so ago, is not common anymore. And but a lot of the more senior drivers that see the truck, actually they get kind of sentimental and emotional. They say, oh yeah, I learned driving on one of those, maybe a Freightliner Argosy, maybe something along those lines, and then they say, well, it's different than it was before, because in the past they were sitting on a rattling engine with a lot of heat radiation up into the cabin. So that's of course not the case anymore. So the truck drives very comfortably, is air suspended, with an air suspended cabin as well. So from a user experience, I think most of our drivers have been very positive about what they experienced so far.
That's great. Dirk, do you have anything to add before we move on?
Yeah, I think the driving experience is be very similar to like a battery electric vehicle, as Ben had mentioned, because you're using the motors and the powertrain. We spent some time with our fueling standard, our subcooled liquid fueling standard, where we our attempt is within that to define protocols for fueling with liquid, and being able to do it with somebody that doesn't need specialized training, that doesn't need special protective equipment, anything like that. And so getting some feedback and learnings on the fueling process has been beneficial as well. And I would say that on the whole, it's been quite positive. So
that's great. So my next set of questions, Hui, these are going to be for you. One of our audience members had asked, why does H2 ICE need after treatment if it's not using carbon-based fuel?
Right. So basically the NOx emissions, right, the criteria NOx emissions is from the combustion, is from the high temperature reaction of oxygen and nitrogen. Right. So despite that we don't have carbon in the fuel, the hydrogen combustion still created this high temperature environment, and lean burn conditions would generate the NOx. However, I wanted to point out the NOx emissions of hydrogen combustion, because this is the lean burn, is way much lower than other fuel we have seen. Right. So the accumulated NOx emissions from the certification cycle is much lower. We do need to deal with some other aspect of the emissions, but yeah, we still need an after treatment, and we can meet the most restricted emissions regulations that existing today. Yep.
Gotcha. Another question for you here. Somebody is also curious, is the catalyst for H2 engines the same package as a diesel? Also, are there particular particulates made by this engine requiring a filter, which I guess is similar to what we're talking about here?
Right. Yeah. So the formulation is the same with our diesel engine, and we do have to put out additional considerations in terms of the after treatment. Maybe just to mention a couple of them. So the size, right? I mentioned this is the lean burn, and so hydrogen need a lot of air, right? The stoichiometric air ratio almost doubles that of diesel. So meaning for the same mass of hydrogen, we need twice the amount of the air at the same lambda, and we are running leaner. So we do need a lot of airflow. So we need to consider the after treatment size, not the formulation, in order to deal with the NOx emissions, and maybe the thermal management we need to consider as well. For the North America, on the particulate matter emissions, we do not need a filter like the diesel does, and that's thanks to the hydrogen fuel doesn't have carbon in it. The only source of PM would be a little bit of oil slip from the normal oil consumption of the internal combustion engine. So we don't expect we need a filter to meet the PM regulation. Yep.
Got it. Okay, that's great. Another question that we received here, and this can be anybody can take this one. How must a garage be adapted to maintain and repair a hydrogen truck?
I could take this since we have been going through the process a couple of times. Or Derek, I don't know. So with regards to hydrogen, it is gaseous fuel, so you have to upfit your maintenance bay with regards to evacuation. So active ventilation systems are necessary. There's also a requirement for roof hatches that open automatically if gas is being detected. So you need to install at certain locations hydrogen leakage sensor sniffers that are basically detecting hydrogen in the air. That being said, you could also service them under, outside. That is also possible, or under a canopy. And then there might be lesser requirements. You obviously cannot do that all year round unless you are in a state that would allow that. But this is basically it. And then, of course, you have high voltage systems on board. So you need also high voltage training for your technicians, and you need personal protective equipment for your technicians. And that's pretty much about it. So and then it's very difficult to make a very general statement here. It also depends on where you are situated. Your local fire marshal want to have something to say here, or other associated organizations that are looking over the hydrogen safety in particular. So, but that's about it.
Got it. Anything else to add?
Not much more to add there. I think to Ben's point with fire marshals and so on, as we get more and more municipalities and locations establishing standards and best practices and so on, that will help with getting approvals on making those changes to the facilities. So,
got it. Great. So we have a couple more minutes here. One question that we've got here. So with everybody's experience in this industry, obviously hydrogen is not necessarily a new industry, but has experienced pretty immense growth in the last couple of years. And as the industry progresses, what are you guys seeing as the cost trends today for H2 delivery? With your experience, do you see things trending more toward availability and affordability, or do you think that it is going to be a while before, or additional things need to happen before we see things more trending toward affordability?
Yeah. I mean, I can make maybe a general statement on that because cost has been and simplicity, let's say, has been part of our super truck program as well. And as we see that research program evolve and mature, we're comparing it to battery electric at this point, not necessarily to diesel, but we do see a path if you can get your optimization right and get your component sizing right, battery sizes, getting your fuel cell size right for the application. This single engine solution that we're looking at as well can reduce the part count. I do see a trajectory where the fuel cell vehicle itself can reach a decent cost point. Will it be as low as diesel vehicles are today? Probably not, because within the cost you've got volume effects that affect what the cost is as well, and not just the part count. But I can see on the vehicle side it trending in a positive way. So,
well, I think the same can be said also about the fuel itself. There are major developments right now underway. There is a hydrogen hub emerging here in California, Arches. So there is government support and an acknowledgement that this is a viable path, a viable energy carrier. But coming back to our deployment in Georgia, so we worked through the business case and the TCO, and we knew the truck price is one thing, but what really matters is to get the fuel price to a near diesel level. And we have done, I think, pretty good work with that with our partner Hydrofleet and 1H2, and are pretty close. It really just depends on inside and outside factors. I'm not saying that this can be replicated everywhere, but I think we can do it in some places to meet our customers' needs.
Awesome.
Yeah, I also want to add maybe a little bit just on that one. And the hydrogen price is high today, I think, but it needs to be much lower than today's price in order for the mass adoption, I think. So hydrogen ICE specifically, I think, is lower cost than other zero carbon technologies, right? So probably can be deployed faster and probably facilitate the infrastructure development. I think otherwise we may constantly think about the chicken and egg. Do we have the hydrogen on the market, or do we have the usage of the hydrogen in the market to encourage the gas producers to bring the hydrogen, make it available infrastructure and the price-wise affordable, right? So for that, I think it's very important for us to think about hydrogen ICE as well.
Absolutely. Well, we only have a couple of seconds remaining here, so I think we will end it here. Thank you, everybody, for sending in your questions. So we will, I guess this is our final closing here on our third hydrogen session. Thank you, everybody, for joining us today. Thanks to everybody who has stuck with us since the beginning of the boot camp back in February. Just a reminder, in 2 weeks, we will be back here for our hydrogen workshop and boot camp finale. Also, remember to go back to the landing page of the session on runonless.com, take the quiz, make sure that you provide your contact information. You'll get some good Messy Middle swag out of that, and connect with us on social media. All of our handles are linked out here. But we so appreciate the time that you've spent with us here today and over the last couple of months. I would like to again extend a very, very warm thank you to our speakers for spending the time with us here today. Have a wonderful day, and we will see you in the workshop. Take care, everybody.
Thank you. Bye.
Thank you.
Thank you.